Welcome to another day on the Journey Chez Chem. Well, today I'm so excited because we're doing lab today. So please do the warm-up questions as quickly as possible, and I'll see you in a moment. Number one is a little bit of review of what we discussed yesterday in limiting reagents. Here we are given an equation and we must first balance the equation. If I have 3 carbons here, then I must have 3 carbons here. I need 8 hydrogens and therefore I will put 4 waters. Now this gives me 6 oxygens, and here I have 4 oxygens, and 6 plus 4 is 10, and therefore I need 5 O2s. So that one worked out evenly, and we like that. Now I am given 4 moles of propane and 20 moles of oxygen. I do my ratio. 1 is the coefficient for the propane, is to 4 moles that I have, equals 5 moles is my coefficient for the oxygen, and I want to know what amount of the oxygen would be required to use up these 4 moles. And therefore, I need 20 moles. And 20 moles is what I'm given. Therefore, I'm going to use up everything that I have. There is no limiting or excess reagent. Both are used up exactly. It's as though I was making cookies and I had exactly what I needed in the house and nothing was left over. So there's 0 limiting and 0 excess in this case. I can use either one of these amounts in order to determine the amount of carbon dioxide in water. Well, I'm going to use the propane because I can see that 1 is to 4 as 3 is to 12. Again, the way I would do that is that I have 4 moles of my propane. There are 3 moles of carbon dioxide for every 1 mole of propane. And I get 12. It is a ratio relationship. And then I could also say 1 is to 4 as 4 is to 16. Again, I could say 4 moles of propane. There are 4 moles of water for every 1 mole of propane. And 4 times 4 is 16. And I was doing it from the ratio perspective so that you can understand that you can look at it and actually see when they're very simple numbers what it works out to be. And if not, you can always do the math and make sure that your moles cancel and get the compound that you're looking for. In the second one of number 1, I am given 10 moles and 15 moles. 1 is to 10 as 5 is to X. I ignore the fact that I have 15 moles of the oxygen. I want to determine, in order to use up all 10 of these moles, what is the amount of oxygen in moles that would be required. X is equal to 50, and I have 15. Therefore, I'm going to run out of the oxygen. Therefore, oxygen is my limiting. And so 0 and 0 is what we had from the first one, and now oxygen is my limiting and propane is my excess. I must always do my math. I can only make as much as is determined by the limiting reagent. Now, 15 moles of oxygen, there are 3 moles of carbon dioxide for every 5 moles of oxygen. And I can reduce that fraction and see that 3 times 3 is 9. I could also look at the ratio and see that 5 is to 15 as 3 is to 9 because I'm tripling those numbers. 5 times 3 is 15, and 3 times 3 is 9. So that's a variety of different ways that you can look at it. And 15 moles of oxygen and 4 moles of water to every 5 moles of oxygen. Again, I'm going to reduce, and 3 times 4 is 12 moles of water would be produced. Now, number 2 relates to the lab, and it says, why do we use water in a calorimeter? Well, the reason that we use water in a calorimeter is because it has a very large specific heat capacity of 4.18, and most metals are much less than 1. 0.3, 0.9, so they're much less than what water is, and water can absorb a lot of heat for the same volume. And that's why we use it in calorimeters. And you know, if you live on the coastlines, that it is more moderate in temperatures. They don't change as dramatically as they do in the center of the country, of a country that is based in a land mass, because land will give up and absorb heat much more quickly than any areas near oceans. So we use water in calorimeters. Okay, now, I'll see you in the lab. Oh, how much I love lab. And here we are again. And now we're determining the specific heat capacity of 3 different metals. Now, I must measure the mass of each one of the metals. And the first one I will measure is tin. I place it in the middle of the pan. And it began at 0, and now it's 69.62 grams. 69.62 grams of tin. Now I will measure the mass of my copper. I place copper in the middle of the pan, and the copper is 70.91 grams. I identify copper, and 70.91 grams is the mass of the copper. Now I will measure my third metal, which is aluminum, and the aluminum is 66.83 grams. 66.83 grams, and this is aluminum. Now I also need the mass of the calorimeter, which is 2 styrofoam cups. I place 2 styrofoam cups on the balance, and it comes to 8.46 grams. The mass of the cup is 8.46 grams, and that will be the same for all 3 metals. Now I am going to pour the water into the cup about halfway. It's not critical how much, and I will get the mass of the water and the cups. And the water and the cups is a little bit too much for my balance. Still too much for my balance. $170.46 grams. 170.46 grams of the cup and water. Now we get to go play with the Bunsen burner. I'll see you there. Here we are, one of my most favorite places. Now, I am going to go ahead and place these 3 metals in the water while it's cool. It makes it much easier to do when I don't have the Bunsen burner going. And then I will turn on the Bunsen burner. I have the gas going, and then I must have a spark, and boom, there we have flame. And I put it underneath. Now, as soon as I see bubbles, I know that the water is boiling. And I will need to get the temperature of this boiling water, and that will be the temperature of my metal. it shouldn't take very long for the water to come to a boil. It's not a lot of water. And I need to know the temperature of the metal, and I also need to know the temperature of this water. So while I'm waiting for the water to come to a boil, I'm going to go ahead and get the temperature of the water in the cup. I need the original temperature of the water in the cups. And it seems to be 22.0 degrees Celsius. 22.0 degrees Celsius is the temperature of the water in the cup. And the information you need to solve this specific heat of each one of these metals is given in the very front of the lab. It goes through the method by which you would do that. And then yesterday's warm-up also discussed that. We did exactly the same thing as we're doing here. Now we're just doing it for real instead of in a data table that you're given the information. Now we're determining the information together to determine the specific heat capacity. And as I said before, this is one of the most fundamental types of reactions of finding specific heat. And maybe that you've done this before in another science class. But sometimes it's good to redo these things, and we get a greater understanding for what heat is and what specific heat capacity is. And it shouldn't take very long. We've covered, in this topic, we've covered limiting reagents, excess reagents, mass, using balanced equations, and remember, you always have to know those decompositions and what the products are of those decompositions. And the next time we meet, we're going to talk about enthalpy, and enthalpy is heat. And we're going to learn how to determine the enthalpy of a reaction. And that's the last thing that we'll learn for this topic, and then we'll review. And you know that I sometimes have difficulty being patient and waiting for these things to react or boil. It just requires patience, and chemistry requires patience in the lab. Now, I could go ahead, if I were a student, I would go ahead, and while I was waiting, I would determine the conclusion questions and the further investigation questions. I will determine the theoretical specific heat capacities from a textbook, and I will give you those values for these three metals so that you have them in case you cannot find them in a textbook. I will give them to you, and that will help you in doing the percent error. Now, we're going to have a large percent error because I will lose a lot of heat as I'm transferring this metal into the styrofoam cup. Metals are such very, very good conductors that as soon as I remove it from the heat source and put it in the cup, I'm going to lose a lot of heat. And you've probably noticed that maybe while you were cooking or grilling out. You would notice that when you use tin foil, oftentimes the edges are actually cool when you take it out of the oven. Oh, I see a bubble. We'll let it go a little bit more, and by the time I really see a lot of bubbles, I'll know that I'm at the boiling temperature. It is indeed boiling. I see the bubbles forming at the bottom of the beaker, and I see bubbles going around the metals as well. And I need to know what the temperature of that water is. And we're going to learn in the next topic why once the water begins to boil, all of the energy goes into its boiling and the temperature will not rise. It is on a plateau because it is changing from the liquid to the vapor state. And I don't want to touch the bottom of the beaker because that would conduct more heat and make my temperature, whoa, that's going up fast. That is incredible. It's so neat to look at that thermometer and how fast it's going up. I'm keeping my eye on the thermometer as I want to know when it tops out. Now, there are methods by which I could clamp this thermometer into the water and I wouldn't have to hold it. But for my purposes, I think it's fine for me to be holding it. And it's leveling out now. At 94.0 degrees Celsius. 94.0 degrees Celsius is the temperature. Oh, it's going up a little bit more. 94.5 degrees Celsius is the temperature. And you can tell that I'm at a higher elevation because at sea level it would have boiled at 100 degrees Celsius and it's not boiling at that temperature. 94.5 degrees Celsius is the temperature of my boiling water, and I want to record that. 94.5 degrees Celsius, that would be the temperature of the metal. Now, I am going to take the metal and I want to put my thermometer back into my calorimeter, and I'll give it a chance to go back down. And because there's such a large possibility of losing so much heat between the beaker and the calorimeter that we would not grade this one on accuracy. We just want to go through the process and understand how we determine the specific heat capacity of this metal. Now, I am back down to 22 degrees Celsius for my initial temperature of this water. I am going to remove the tin and as quickly as possible put it into the cup. Now, the temperature will increase I'm watching it. To 23.0 degrees Celsius. 23.0 degrees Celsius is my final temperature of the system. Now, I am going to remove this metal and put it on my lab station. And I'm now starting at 23 degrees Celsius. So my new temperature of my system for the not of the system, of the water for the next one is going to be 23.0 degrees Celsius because it's absorbed heat from that metal. But I'm going to continue on using the same calorimeter. Now I'm going to take out the aluminum, and notice that I put it up high next to the Bunsen burner so I can quickly put it into the water. And for the copper, this is the copper because it's the orangish reddish one, and it is going up I want the highest temperature at which it's going, and that would be 24 degrees Celsius. 24.0 degrees Celsius is my final temperature of that system. And again, I'm going to be starting at a higher temperature because this metal has put its heat into the calorimeter. And therefore, my initial temperature now is going to be 24 degrees Celsius. So the temperature of the water now is 24 degrees Celsius. 24.0 degrees Celsius is the temperature of my water. Oh my. I see that it's gone up to 25 degrees. So my initial temperature here is going to be 25 degrees. And my final temperature of the system for the copper will be 25 degrees as well, because it did increase. Now, finally, I'm going to put my aluminum in, and I'm quickly going to put the aluminum into my calorimeter, and there we have it. And I can turn off my Bunsen burner and observe this temperature. 26, oh, it's still going up. 27. 28.0 degrees Celsius is my final temperature for the system. 28.0 degrees Celsius is the final temperature for this system. And the system is the styrofoam cup with the hot metal. And that's the data that we needed for today. And that's all you need to do. Have for the write-up then, you have the data that you need. We determined it all together. You now can see how we use styrofoam cups to be our calorimeter. And we made the metals the temperature of the boiling water, and then we put them into our calorimeter. And we will need to get the change in the temperature of the water. It went from its original temperature to the final temperature of the system. And then the metal went from the boiling water to the final temperature of the system. And if you look at yesterday's warm-up, that should help you as well. Well, that was some fun. I get so excited at doing lab. And thank you for being here, and I can't wait to see you tomorrow.